SNR. Signal to quantization noise ratio. Now, if I have a, say I have a transmitter here, let us suppose. I have a channel here. Receiving antenna and receiver. Now you tell me where actually this SNR will be calculated for a simple communication system. I repeat, for a simple communication system, where actually the SNR is calculated. I have two blocks here, one at a transmitter and one at receiver. Again, I have to ask by name, I think. B2. B2. E2.
Yes, sir.
You tell me where actually this SNR is calculated.
Signal to noise ratio is calculated at the receiver.
Receiver. So you want to calculate at the receiver. Okay. Can you tell me why? Your answer is correct. Tell me why we need to calculate SNR at the receiver.
Means we at the receiver only we'll get the output signal, no sir.
Okay. So what?
Sir, I don't know properly, sir, the correct reason.
Any other answer? Anyone else? See, at that,
Side
come again. Somebody is telling something.
noise get added in channel, no sir. That's why at the receiver we will calculate the signal to noise ratios.
Who is responding? I know who is responding.
Early 422.
22. Perfect. Noise is added in the channel. Excellent. At the transmitter, signal power transmitted, let it be ST. Noise is added in the channel. At the receiver, I can have my input signal to the receiver, let it be SI, as well as noise input to the receiver, let it be NI. Now at the output of the receiver, what is the signal output power and what is the noise output power? Now for the time being, if I assume my ST equal to SI equal to S naught, there is no variation in the signal power. Whatever the transmitted signal power, the received signal power is same. My receiver output signal power is also same, let us suppose. Then the performance of the receiver is dependent on SNR, where it should faithfully reproduce the signal at the output, suppressing the noise or decreasing the noise component at the output. Doesn't matter how big the noise component at the input, thereby maintaining a high value of SNR. So these are the basics of SNR, and the performance of any receiver is figured out in terms of output SNR of the receiver. Okay. Now, my signal, let my signal is from VL to VH, the same example or that we have taken. Let it be some or say minus V2 plus V, let us suppose. In between my signal is there. Maybe something like this, let us suppose. Now the question is, no doubt we divide into different quantization levels. Let it be M quantization levels. And each quantization level has the step size of S. So from here to here, there is S. From here to here, S. From here to here, S. So on up to the final value. From here to here also, yes. That means the total voltage swing from minus V to V is given by, what is the total voltage swing here? From here to here, what is the total value?
Two V.
Total voltage swing is 2V. Fine. Now here in terms of quantization levels and step size, I have M quantization levels. Each has a step size of S. Okay. So therefore, my 2V must be equal to M times S. Am I right or not? Is this clear? Okay. Is this relation okay or not?
Yes, sir.
Fine.
Yes, sir.
Okay. Now I want to calculate the signal input power. To do that, I need to have the probability of occurrence of the signal in this region, in this quantization region, or in this, or in this, or in this, anywhere. Let us assume my signal is the signal is having uniform probability density function. That means my signal voltage will occur equally in all the levels. That means the total swing is 2V. Therefore, my f of m, probability density function f of m, can be given by 1 by 2V. This is the uniform probability density function. Occurrence of the voltage is equally probable in all the quantization levels. Fine. Now, my signal input power is the mean square value of m of t. Mean square m of t. Mean square value of m of t. So I can integrate. The lower limit is minus v, the upper limit is plus v. Probability density function of m of t into mean square or square of m of t dm. I repeat, my signal input power is the mean square m of t, which can be expressed as the lower limit is minus v, the upper limit is v. Therefore, integral minus v to v, probability density function of m of t into m square dm. Now we know that probability density function f of m is 1 by 2b. To substitute that value, I'll get 1 by 2v integral minus v to v m square of t dm. So that will be equal to 1 by 2v. Evaluate the integral. So you will get m cube by 3 per minus v to v. Substitute the values and tell me what is the remaining. Substitute the values and let me know what is remaining. You know how to substitute, right?
V square by 3, sir.
Okay.
V
So
square.
signal input power, you got v square by 3. Okay. Yesterday we have calculated the quantization noise. Do you have any idea? We have
S square.
calculated s square by 12, right? So my quantization noise is NQ is mean square error, that is S square by 12. So this derivation we have done yesterday. Now we have calculated input signal power. So therefore, signal input power divided by quantization noise ratio, that will be SNRI equal to SI, you told V square by 3, sorry, V square by 3 divided by quantization noise is S square by 12, right? V square by 3 divided by S square by 12. Is this clear?
Yes,
Okay.
sir.
Okay. But let us go back little. Yeah. Here we arrived at 2V equal to MS, or from which I can say V equal to MS by 2. So substitute this value in place of V and tell me what is the final expression.
M square, sir.
Final expression, you got M
Square.
M square. Okay, M square. Okay. So you got final expression as M square. So signal input power divided by quantization noise power is M square, where M is the number of quantization levels, which can be expressed as M equal to 2 power N, where N is the number of bits. Where N is the number of bits. Right. Now, just before I assumed that my transmitted signal power, received signal power, and output signal power are same. Okay. So therefore, my signal input power is same as signal output power. Therefore, my output SNR, signal output power by quantization noise ratio, SNR output is also equal to M square. That can be expressed as 2 power 2n. If I substitute 2 power n here, M square will become 2 power 2n. So if I want to express this SNR in dB, SNR output in dB, so S naught by NQ in terms of decibels can be expressed as signal power, noise power. In terms of power we are speaking, therefore 10 log 10 M square, that is 10 log 10 2 power 2n. So it can be written as 10 log 10 2 square whole power n. So n will come to the first. So n into, you have calculators with you? 10 log 10 2 power 2 is 4. Can anyone evaluate this and tell me 10 log 10 4? Or let me Yeah. 10 into log of 4 is 6.02, 6.02, or I can approximate it as 6. So therefore, equal to 6n. My SNR output in terms of dB is 6n. This is the final expression. Clear?
Yes, sir.
Yes, sir.
Okay. Now, if I take a typical example that in the previous case we considered 8 levels, right? 8 levels. During the PCM modulation, we considered 8 levels, level 0, 1, 2, up to 7. 7 codes are there, 8 levels, M0 to M7. So, for these 8 levels, second, how many? 8. Excuse me. We arrived at SNR value to be SNR value in terms of dB is 6n. And the considered example, my M value is 8. Means that your n equal to 3. So for this 3-bit representation, my SNR, whatever the considered example, my SNR will be 6 into 3, that is 18 dB. Assume I have 256 levels, quantization levels. This 256 can be represented in terms of say 2 power 8. So my n value is 8. So SNR output in dB, signal to quantization noise ratio, is 6 into 8. That will be 48 dB. Now try to observe these two figures, 18 dB and 48 dB. 18 dB and 48 dB. When you increase the number of quantization levels, the signal to noise ratio is increasing directly. If the number of quantization levels are less, my signal to quantization noise ratio is also less. This is what we have seen in the earlier. By appropriately choosing the S value, step size, if we choose a small value of step size, which leads to a large value of M, a large value of M will lead to a large value of N, a large value of N leads to no doubt an increased bandwidth, but SNR, I got a very good SNR, a high value of SNR. Even though bandwidth is increased, we got a high value of SNR for a decreased value of step size. Keep remember, because step size is decreased, the number of quantization levels increases, the number of bits required to represent also increases. Thereby, we can increase the signal to noise ratio, signal to quantization noise ratio. Of course, at the cost of increase in bandwidth. Actually, it should not be at the cost of increase in bandwidth, but okay. Clear? Up to this point, signal to quantization noise ratio?
Yes, sir.
Okay. Now let us move to the very next topic called compounding. Sometimes what happens is, assume my input signal value is is more than 2V, let us suppose. If it is more than 2V, okay? Just little more than 2V, let us suppose. Just little more than 2V. But we have fixed the number of quantization levels. We have fixed the number of quantization levels. And my signal is, instead of minus V to V, my signal is something like this. A little more than V. I designed my everything, my quantizer, PCM, encoder, everything. But fortunately or unfortunately, the input signal size is a little more. Now, as a result, there will be some loss of information, and it should not happen.